Okay, we'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask me. Okay, I'll recap whatever we covered last week and then start today's topics. So today we'll be learning about lambda functions. Okay. So yeah, before that, I'll just quickly recap whatever we saw last week. Right. Okay. Yeah. So starting with type ID. Yeah. So let's say you have variables A, B, C, and that we have defined as some integer, double, and float. So each of the data types, you can actually get the name of it, as in if it's, so let's say a given variable is a certain inbuilt data type like integer, double, or float. Yes, while defining it is known at compilation time, but sometimes you might have templatized code or you have used macros to have conditional compilation, or you used const expressions to have conditional compilation. So in those cases, it is very much possible that you do not know the compiled uh, the data type of either of these variables. Okay. So in those cases, it is possible that you want to check the data type and then maybe go a certain direction. So type ID is useful in that case. It takes the variable and then using the member function name. Okay, so you access that using dot name function, and that gives you the name of the function. So it's for A, it is integer. For B, it's double. C is float. Okay, so you get the initial letters I, D, and F. Okay, so that's what we saw last week. Uh, Coming to a very important concept in C++ is the auto keyword. Essentially, it is letting the compiler decide what should be the data type of a given variable at compilation time. It will throw an error if it can't figure it out. Okay. A lot of the times, the return type of whatever is on the right hand side to the equal to, right? So based on that, it decides what should be the data type of the left hand side. That's essentially the idea. Now, because of this, you can actually write C++ in a very Pythonic like way. Okay. It's possible, but overdoing it is not really recommended because then you do not have any clue about the actual data type that a given variable has. Okay. There is a balance. Sometimes it's really useful, like this example, like we see here. Okay. So let's say we define a map. So, okay, I'll go through this small example anyway. So let's say x equals to 7. Okay. There, the right hand side is an integer. So auto decides what should be the data type. So that we confirm by using the function that we just covered before. Okay. Next, we use the standard map data structure. Okay. Define a map. I'll just name it as in capital M. Okay. So this is my map now, right? Where the two templates are integers, as in it takes the key as integer. Okay. And the connection to it. So the key and value pair, right? So maps, so recall how maps work. Essentially, they are a key value pair, and a set of these key value pairs is essentially a map. Okay. So you basically relate a key value, uh, something called a key to something of a value. Okay. So it gives you the starting iterator. The data type of such iterator will look something like this. So it is standard map. You have to give the template that I've used for the map while construction. Okay. Then use the uh, double colon, okay, to access the iterator. All right. So basically it becomes sort of a namespace for it, and then you access the iterator. Then you give the name of the variable. So let's say I'll just call it map begin, and right hand side map.begin is the actual function that I'm calling. Okay. Instead of writing all this, which honestly, as long as I know that I have a map and all this templatized things is not really necessary, as in I do not need to worry about it. Okay. Because after a certain point, because of this long namespaces and templates, it is actually harder to read and see what the code actually is doing. Okay. So in these cases, it's actually better to just use auto. Okay. And we really don't worry about how the begin, what the exact data type it returns, but we roughly know that it's the begin function and it's an iterator to our map. And our map is of certain data type that we um, automatically will be taken care of anyway. Okay. So a loop would loop something like this. Okay. So where you have a iter, okay, variable, which is of this data type, right? Takes the begin function's return type, okay? And until the iterator is not the end of the map, okay, you keep iterating. That's essentially the for loop function that we have, okay? Now, the auto here makes it much smaller, right? So you can just put auto and then done. The intention of the programmer is also clear here. So it saves on reading too much of code where not much is saved, right? So auto is pretty useful in these cases, right? So after this, you access the data inside the map through the iterator in this way. So essentially, iterator is like a pair. So you access the first element using the, so iterator, you can think of like a pointer. So you're using the arrow function. With the first, you get the key part of the pair. And with second, you get the value part of the pair. Okay. So the two values you access through this way. Okay. Next, let's say there is an X and you can easily just declare another Y. Okay. Using the auto function, you don't need to worry about what the X is actually is because you just want a copy of it. Okay. So in these lot of cases, auto is pretty useful. And then you qualify that auto with more types. So more qualifiers. For example, if you want it to be const qualified, you actually have to add it. Auto does not take constness or constness pointer or const reference. Okay. In those cases, you have to actually specify it. Okay. Auto only takes the primary inbuilt data type or the primary um, custom data type that we define. Okay. Similarly, in these cases, taking each of them, you can take the name type ID and then check the name. Okay. So taking this as the inspiration, if auto doesn't do that, what if I want some kind of function which does exact data type uh, copying? So that's exactly where decal type comes. So let's say a is an integer and p is a pointer, but of integer data type, as in pointing to integer numbers. So I have decal type a, b, okay, so I pass a to the decal type, it will see the data type of a and return integer because that's the data type of a. Then this whole thing becomes integer b. Okay, so yeah, this whole thing essentially becomes a declaration like integer b, very much similar to what we have here. Okay, if I pass p here, it knows that it's a pointer, so it will actually return the integer pointer, and q also becomes an integer pointer. Okay, so in these cases, decal type is pretty useful. Okay, depends on what use cases you want, essentially. So we take another example here, which should clear how each of the type works. So define a as 10. So a is an integer. Int ampersand b. So this is the syntax for a reference. So integer reference b. Essentially, a and b are being the same variable then. Okay. Just that we are, we are using another name for the same a. Okay. Then I declare const c, right, equals to 11. So c is now a const integer. Then I have const integer ampersand b. So it's a const integer reference, okay, which takes c, and similar to b, d is just another name for c. Okay. What if I declare auto a, b, c, and d? And on the right hand side, I set them to a, b, c, d. Okay. In each of these cases, because the base data type of all of them are integers, so auto a, b, auto c, auto d, all of these will become just integer data type. Okay. Right. Okay. Then you can do some other things like change B and change auto B. So this is basically to confirm what we just saw. You don't have to take my word for it that auto underscore B is not a reference. Like it's not of integer ampersand. It is just integer. To check that, set B to 1. Okay. So that should, because it's a reference, it should actually change A, right? So change set auto B to 1 and then print A. Okay, you'll see that only this line will change it, but this line does not. Okay, because if auto underscore b was a reference to b, which itself we know that is a reference to a, changing auto underscore b should also change a, right? But it does not. Okay. Similarly, you can change c and auto underscore c. Okay, and try to play around with that. Furthermore, I declare, let's say, a variable called vr. Okay. So that I'm declaring it as an auto reference to A. So here particularly variable var is an integer reference because I explicitly put the ampersand. Okay. Next, I write const auto ampersand var2. Okay. So essentially it's a const ref it's also a reference to A, pretty much similar to var. But the difference is that var can change A, but var2 cannot because it's a const reference now. Okay. Next, we declare the decal type version of the same thing. Okay. Essentially, what we did for the auto data types, we do for the decal types. So you can see that passing A, B, C, D to decal type will actually return their actual data types. So for example, here A will return A integer. Okay. So that's the data type of what decal underscore A will be. Okay. So first is integer. For B, it will be integer ampersand as a reference, const integer, and a const integer reference. Okay. Next, we declare E as 12. Okay. And what if I decal type E? So the return will be integer, unsigned integer, right? So I'm setting a unsigned integer F to -12. Ideally, unsigned integers can only take values from 0 to some very large positive number, right? So essentially, it's only positive numbers allowed. It's not signed. Okay. So because it is not signed, it doesn't have any concept of negative numbers. Okay. So printing this, you'll see that there is a uh, sort of a wrapping around that happens. I'm guessing it's underflow, but in any case, yeah. So in any case, this happens because this is the behavior of unsigned integer. You try to subtract 12 from it. Okay. So it will just wrap around to the very large number, which can be represented using unsigned integer. Okay. All right. Next, initialize a list where the reason to declare this is essentially this one. So let's say I have integer integer one is integer, right? Yeah, sorry about that. Yeah. So continuing, let's say I'm setting int a as 1. So 1 is an integer. So using auto here, make sure that it is integer. Like at compilation, it is declared as integer. Okay. The other way you can do the same thing is use the brackets. So you have your variable, then pretty much like you're defining an object through a constructor. Okay. So the integer class sets itself to the value you are passing. Okay. So pretty much the same syntax as object-oriented programming. Okay. But now you can think of it like you have an integer class now. You declare the variable b and set it to 2. So pretty much the same syntax for both of these. As in, they do the same thing, but different syntax. Okay. The other way is if you don't use this small parenthesis brackets, but you use the curly braces. In that case, it's the initializer list. Okay, so don't get confused. So initializer list is essentially a single data type. Okay, so the data type will be something like standard initializer with a template. So the template decides what the data it actually contains. Okay, so it's basically a collection of a certain data. Here it's integer. Okay, so because all these are integers, so the init list is also an integer while a also takes integers, right? So because of that, a being an integer, the initializer list C is also standard of data type standard initializer list with template integer. All right. Any questions so far? Okay. All right. Moving on, we'll cover another very important topic called lambda functions. So let's start with some examples. Let's say I have a const integer m as 10. Okay. And I will write the main function, something like this, with standard cout remainder. Okay. So essentially, I want to write a remainder function. Okay. Which returns when a certain number is divided by another number, essentially. Okay. Which I will make it like something like this. So let's say it's 15. And that in the function. Let's write this remainder function. Okay. So should also be an integer return. Okay. And itself takes n, right? Just needs to return n percentage and sorry, yeah, n. Okay. Now, the interesting thing here is that what I'm passing is the number to be divided by. So the n is the number which we are dividing. Okay. And the divisor is m, which is constant. I fixed that with the const global variable. Okay. Excuse me. Yeah. So yeah, we know that the answer will come out to be 5. Okay. There is 15 we are passing, dividing by 10. So the remainder will be 5. So we know that. Now, what if we, so, okay. The way we'll see this is the same function, but we wrote a complete function separately to do this. Okay. Now let's look at some other examples and then I'll try to motivate lambda functions from this. Okay. So another way you can do the same thing is so include string. I use structs this time. So any variable defined without um, the sorry, what I meant is by default, all the member variables are private inside a struct. Okay, so we'll just use that sort of a constructor for this struct. I'll use the same name. Okay, so this is a constructor. It will take input as underscore n, okay, and set the interim variable m to be to that which is the input. I'll leave the body of the constructor empty and define the operator this, okay, as integer n. Okay, so pretty similar to the one that I had here. All right. Return n percentage m. Okay. Now coming to the main function. Struct. I'll call this remainder with rem. Okay. So it'll be the object, and remember, because the constructor takes m here, which will be constant for this private number, right? We're not setting it again and again. The reason being, the only way we set this m is through the constructor, and that only happens while when the object gets constructed. Okay, so that only happens once. So the behavior will be very similar to the one that we have here, because we set m to be constant and it to be 10, right? So passing 10 here does pretty much exact same thing as before. Furthermore, uh, it behaves exactly same, but the way we do it is slightly different. Okay, so here we're using structs to do the same thing. Okay, right? And I'll define the cout using the rem. Now it takes 15. So the rem, don't get confused. So when you have the initial rem with 10, this function gets called because the constructor that gets called. Okay. So struct remainder struct as in we want to say what we are actually calling. So we call it then yeah, we call it the name struct and the actual name of the class or the struct. Okay. Then the object name and pass the initial value for the underscore m. So m gets set to 10 here. Later, when you call in the object with the bracket of any of these values, okay, there this function bracket gets called, as in which we define with the operator keyword and then give the symbol of it, okay, which takes input as integer capital N. That's exactly what this is. Okay. Essentially, what I'm trying to say is first time you call it, constructor gets called. Second time you call it, the operator function that we wrote gets called. Okay. Now this one seems very similar to the one here. Okay. So I can maybe write it as a reminder as a rem function. Okay. Whatever the name of the object here, but you get the idea. So the remainder 15, okay, is the same line as here. Okay. All right. Printing this will result in the same output. I think I should show that. Okay, so the output is 5. That's what the remainder should be. Okay, and if we run lambda2 function also, we get the same answer. Okay, right. Let's take another example. Okay, so the class this time we use something called a functor class. Okay, first one is a pure function we use to the get the remainder. Second example is using struct. Okay, third example will be we'll use a class. Okay, but specifically it's a functor. I'll explain it more. Okay, so it is essentially a class itself. Okay, but behaves like a function. I'll define a public member operator. Okay, in struct your functions are public here. Okay, the data members are private. Okay, integer n return that's fine. Integer operator brackets n return n+4 integer increment n um, so the name. Okay. So now the class is set up. I'll define an object of this class. Okay, call it func. So this is a functor now, and the name of the class is functor. Okay. So let's see some examples as to how do we use this. So first of all, functor print with small brackets. Okay, so that is simple. We pass func with 5. Okay, next we use the big brackets. Okay, so this part we'll call the first definition. Second one we'll call the second definition. Okay, because this is the operator that we're using. Okay, and then next we are calling the increment operator. So that you call by using the increment and then passing the value. Uh, but remember, there's a function, so you have to use this definition because remember the brackets. Okay. Similarly, you have to use this one, and that's it. So what this essentially did is, remember, I mean, usually, if one recalls in the first example also, a function, full-fledged function, looks something like this. So you call the function, give the small brackets and give some input. Okay, so this is what this signature of a function looks like. We did something similar here. Okay, we got that function signature, but we used a class object to get that. We sort of wrote a definition for this bracket, okay, to get us this the desired output. Very similar to that, we are also using this function. Okay, there was an object of a struct. Here it's an object of a class, a functor. Okay, I'm using func. Okay, passing 5 to it. All right, I'm essentially using the object as a function. So it's a functor. So that's what a functor is. It's a class which behaves like a function. Okay. I can go even further, use the capital brackets. So remember the capital brackets are usually used to get the data at a certain location. So you want to dereference or essentially you're getting a data of a standard vector, let's say, the ith position value. Right. So there, in those cases, you might have seen the capital bracket being used, but it's not necessary that you have to, that's how it always behaves. Your functor can have its own definition of for the capital brackets. Okay. Third thing is essentially a simple plain function where you call that function using the dot function, pass the input, and you're done. Okay. All right. Okay. So that covers functors. Okay. Now let's take another example. This time it's the actual lambda expressions. So I'll give the syntax for it. So lambda expression looks something like this. First, the uh, big brackets. Okay. So that part is called the capture list. Then we have the parameter list. Then the return type. And then inside the curly braces, you have the body. Okay. That's it. All right. So could look something like this. So auto check print equals to doesn't capture anything, doesn't take much of an input, but the body looks something like this. And just a simple hello world. Okay. Now coming to the main function, auto. Okay. I'll define the same thing. So this is how a normal print function using the lambda expression will look like. Okay. So you can have full-fledged functions like this, okay, where you call it again and again later. But sometimes you want a throwaway function, okay, and do not want to make create it outside the main, okay. In those cases, you can use lambda functions or lambda expressions. A simple one will go into each of the parameters individually, but think of this case as when print gets called, okay. it prints, it executes the body part of it, where currently this body has a hello world function, as in just a print for it. Okay. All right. Now, to use this lambda expression, it behaves pretty much like a function. Okay. So you use the name and use the small braces to call that function. The number of times you call, number of times hello world will get printed. Okay. Let's do that. Printing of maybe I should print 3 hours. So okay. So for 5 here, the output was 5. 5 with this bracket, it should be 9. So that's what we get. The increment as +1. So has 6. Okay. Then, yeah. So auto, right? We're calling it 4 times here. So let's see the output. So print gets called 4 times. So as this body gets executed. All right. Okay. One can also go a little further, as in we stored this lambda expression inside a function and called it multiple times. Okay. You can also do it this way, as in this is a lambda expression, right? As in this whole thing is print, right? And here again, auto is pretty useful, so we don't have to worry about what the return data type is for this lambda expression. It will just work. Okay. So that thing which we used print, okay. So I'm going to substitute this here instead of print. So to call this function, lambda function, I just have to add another bracket. Okay, then I'm done. This will print hello world. So since I'll just comment this all of this. So to show you guys, nothing will get printed this time. Okay. Okay. So lambda 4 does not print anything. Okay. But if I have this expression, it will print hello world. Okay. I do not, then doesn't print anything. And what if I have just this expression, but this time I'm not just leaving it declared, but I'm actually executing it. So calling that function, you need this extra small brackets, which is exactly what we had here. Let's do that. Yeah, so you see it prints once because it gets executed once. If I have everything, then also it will print, but prints 5 times now. Okay. All right. Any questions? We'll have include and for example, the main function. So lambda functions we can even um, have inside if else parts. So let's look at an example. I'll start the if part. Okay. So here was the capture list. Okay. So we'll go through each of them one by one. I just want to show you how lambda functions get used. Okay. So it takes A, takes B, okay, as 2 parameters. So capture doesn't have anything, but parameters there are 2. Okay. And then the body of the function. It returns A equal to B. And then end the body. Okay. Here, now this is a lambda expression, but to execute it, I have to pass some values. Okay. So I'll pass, let's say 8, 8. This ends the if statement. So remember, this whole part is the lambda expression. Okay. actually this is the lambda expression. To execute this function, I'm passing this parameter to it. Now this whole thing is inside the if block. Okay. So that post statement. So if it is true, so the return will be a equal to for a equal to b. So it's a comparison function. Right? So whatever is the result for this, true or false, will get returned to this lambda expression. Okay. And that is the input for if. So if it's true, then we'll execute the true part of the statement. Okay. If it's not, let's say if it's false, then I don't need any inputs, so I can just put it like this. It's false. Okay. Another thing, let's fancy out. Let's say I write another uh, function. Let's say lesser of 8 comma 6. Then I make another lambda function. Okay, so pretty similar to the previous one, but this time the body will just be slightly different. Return a less than b. If it is true, then you return a, else you return b. Okay, pretty straightforward. So this is the body of the lambda expression. Okay, so this is the lambda expression. And to call this lambda expression, I'll give input 8 comma 6. Okay, now this whole thing is what will get evaluated. Okay, out of 8 and 6, whichever is lesser, will get returned. And that is the output for which that's how I want my expression to look like. Lesser of 8 and 6 with this lambda expression, and then this and the line. Okay. Right. Let's print this and see. Right. It's a true statement because I passed 8 and 8 here. So the true statement gets printed. Excuse me. And for the second one, where I have lesser of 8 and 6, because if I compare 8 and 6, 6 is lesser, so 6 gets returned. Okay. There are other ways you can use, sorry. There are other ways you can use lambda functions. So as you might be seeing, return was quite useful before, right? To define this lambda expression, we'll use that again. Let me call a variable called clause. Okay, so lambda. It's again, this will also be lambda expression, and I won't need to worry about the data type. Okay, so I'll use auto, right? Then the integer capture list, so which again will be two integers a and b. Okay, which returns a equal to b. Essentially, we'll do the same thing. Okay, what we saw here, but a little cleaner way. So this needs to end, and the body also needs to end. Yeah, because this is lambda expression, right? So that itself needs to end. With the story, we'll want to refer it to inside the clause variable. Okay. With the if clause, if sorry, and I can just call this function again. Clause will pass, say, my command. Okay. then true statement, else false statement. Okay. Then I have another part where I call this same class function. Okay. But this time, instead of 99, it will be 89. Okay. Right. So the usefulness of this is that the if part that one wrote, okay. So one doesn't, let's say you want to use it only in a certain region of the code. So you can just have a single variable declare to it and then you reuse it multiple times. Okay. Or you do not even do that and just plain use it. And after that, if statement is done, that function gets, it's just not exist anymore. Okay. Right. Okay. Now let's use the same idea, okay, to build the example that we saw in starting. I have the main function, which n is 10. Okay, so auto remainder, the capture list is m, variable takes is m. So the return will be n percentage n, and after n this, yeah, that should be. Let's say I want the remainder. Okay, so I use the lambda expression, pass again, put into it, and n as 10. Okay, standard intel. Okay, let's see how this works. Awesome. So that gives me 5. Now you might notice previously I told you about capture list, then parameter, and then body. We saw the body before. Okay, so that is essentially what the lambda function does. Okay, so that's the body. Parameter is something it uh, expects to change, as in each time you call the function or the lambda function, it expects that this will be parameters. So it will take different values. Okay, so that's the and okay. The capture list is something uh, which it expects to do not change. Okay, as in, let's say I define m to be 10. So once it so I specifically say that you capture m. Okay, so it captures the value that that variable actually stores right now. Okay, so 10 gets captured. Okay, and for the body, the value as of m does not change. Each time you call remainder, capital N might change, depends on what you're actually passing, but the value of small m does not change. Okay. To show this further, so let's say I change this to I okay. So I'm dividing 15 by 5 now and checking the remainder, right? So that should give me 0 expected. Okay. Now let's say I do this line here. Okay. I had 10. I set it to 10 and then 5. I'm setting it outside. Yeah, that will be difficult. Okay, so I'll just set it here. I can't redeclare it. Yes. Yeah. So say it is 5 because m was captured to be 10. Okay. Even if I set m to be something, so here I had captured m for the remainder function, but even if I call remainder and set m to be 5 before that, it does not matter. Okay. Because, so yeah, because changing m to be 5 does not affect the answer here. Reason being, m was already captured to be 10. Okay, so even if I change 5 here, calling this remainder function will not see m, the new m, because m was already captured. Okay, so I hope you understand the difference. Lambda function has 3 parts. First is the capture part, which whatever values it actually takes, that stays the same. Okay, the parameter part, where whatever value it takes can change depending on the number of times you're actually calling that function. Sorry. And then you have the body. Okay. All right. Furthermore, let's say I call this lambda function plainly. Okay. And instead of returning, let me just print it. Okay. So n m it will be taken from the lambda function. Okay. Using the bracket, I just have plus 15. All right. That's it. So pretty much the same thing that we did here. Declared m, declared the lambda function, and did the output for it. All can be also condensed into a single line. Okay. And if this time I try to print the value, so the first remainder will be 5, okay, for this guy. But for the second one, it will be 0. Okay. Remember, this is another lambda function. Okay. It might look pretty much like this lambda function. Okay. But this is another lambda function. And for this guy, m has been set to 5. So it captures 15, dividing 15 by 5, hence we get 0. Okay. So the important thing to remember is for lambda functions, if we say there is it expects input, you give the input while calling it. Okay. If you give a capture list, it will take the present value of that variable. Okay. And then that's all it will use for remainder of the times you call this, well, you call your lambda function. Okay. Here it gets executed only once. But if you store it in a name like here, remainder, then you can call it multiple times. Okay. Any questions? Okay. Taking another example, I have, let's say, a temporary integer 0. I'll define a sum function. Okay. This time, the capture is a reference. Okay. Temp as a reference. And then x integer n is equal to n. Okay. And then end the function. Now, here temp is the running value, okay, which will store the sum through the sum function, and is the input for it. Okay, so each time we call sum, we'll be passing some number to it, and that will keep getting stored inside the temp. Okay, like added. So let's starting with call sum 15. Oh, sorry, my bad. Then see out sum printing and just print temp itself. Okay, so let's run this example. So sum is 15. I think that's expected because the important thing, again, some things to note. Temp is declared outside, okay, and then it is passed to sum. So if I want to print temp, it should be accessible. So remember, the rules for scope of a variable is always respected. So temp should be accessible, is passing to it, okay? And yeah, that's it. So sum is also in the scope, so that gets called and everything. So it is pretty straightforward. We call the lambda function, pass 15 to it, okay? So temp is already 0, so that's what temp was captured. And we add 15 to it. And when we print temp this time, we get 15. Okay. What if I call it a second time? Any guesses? What will happen? What will be the output? Okay. Let's print this and see. So you see the output changes. Yes, I did tell that the capture list captures the value of the variable at when you actually call the function, like declare the function. But it also depends how you're passing the value. So in this case, we passed it by value, okay, in the capture list. So it set m to some certain number and kept you using that number for all the n percentage m body. Okay, so here also the same thing, but here we passed temp as a reference. So whenever temp gets updated, that new value of temp is used when we call this some lambda function. Okay. I hope this is different. This difference is clear. Okay. So I have multiple times. We'll keep incrementing with the previous value. Okay. If you had changed it to not 10, okay. So yeah, this is another important thing. If you didn't have it as not uh, just a capture value, you cannot actually modify that value because it is treated as cost. Okay. So modifying this value then actually does not make any sense. Okay. So, right. only allows from change temp. It's change the capture list. It has to be of reference. Okay. All right. We'll take another example. I have string Jamil val. Let's say the value is 0. I'll define another variable called reference for variable. Then auto the lambda expression check. It captures val as the value. Okay. I'll pass red as the reference for the capital list. So basically, this is the capture list. One being passed by value, another passed by reference. Okay. Now the parameters, parameter 1, parameter 2, both being integers, then the body. This time I'll print it, the value, sorry for that. Value gets printed, reference, reference of the value, then parameter 1, parameter 1, okay, parameter 2, that's the value, parameter 2, and lastly, just end the line. Okay, so let's just print this and just compile and run. See, there's no issues. Okay, it's good. Now let's take different examples. So what I'll do is I'll change ref to 4 and call the check function. Okay. So this time I'll pass, let's say 10, 11. All right. Now let's print this. So here we see the value is set to 0. Okay. So that's what this capture did. So it printed val as 0. Okay. Ref for some value. Okay. We change ref to 4. So when it called check, right, it printed the reference because ref was passed as a reference. So it prints the updated value, which is 4. And I passed parameters 10 and 11. So those got printed 10 and 11. Okay, as parameter 1 and parameter 2. Okay. Now let's say I change val to 5. Oh, okay. Let's make some other. Check this time. Okay. With 10, 11. All right. So it's printed. Okay. This time you see there's no difference between these two. Because ref was changed to 4, okay, that does not, we have not touched that, so that one did not change. Okay, that we see here. The next one is if we pass the same parameters, so that also did not change. Okay, so that's actually intentional to show what actually changes and what does not. Even if we change val, okay, it always captures val as this by value. So initially it was 0. Even if you change val later on, it will still remain 0. So this part is not going to change. Okay. So I set ref again, like choose, let's say something like 17. Check 10, 11. Or maybe this time I'll change it to 7. I change the parameters. Okay, so the parameters change, expected. Ref was changed to 17, so ref changed. Val will not change anymore. Okay. Once you define your lambda function, if you pass something by capture by value, that value cannot be changed. Okay, but what about ref? Yes, you can change that. Okay. Okay. So let's say I want to do the same thing. For lambda functions are useful, just want to show you guys. So we do the same thing using structs. TDS it can be. So let's say I have a main function. I define val as 0, ref, no, send at 0. Ref, I'll just let it, not set it now. Struct, check, app. Okay, so integer, val, integer, ref, underscore f. Okay, so these are all just temporary functions. Here, let's say it is a reference. Okay, so the constructor now check underscore f takes the val integer ref. Okay, so val underscore f gets set to whatever the input is to the val. Then, oh, sorry, reference f gets set to whatever we pass here. And yeah, then we just end the body. Leave the constructor empty. Okay. Now I'll write the operator. Okay. Function with, we'll use small letters. Okay. So this time we'll have now the parameters that we saw before. Parameter 1, parameter 2, both being integers. Okay. Pretty much the same as before. We'll have cout, val, give vals. Then, oh, sorry, this time I have to use the term variables. Yeah. So val will be val underscore f. Okay. Then ref underscore f. Okay. Parameter 1, parameter 1, then parameter 2, parameter 2. Okay. Intel. Done. Now to end this struct. Okay. Now inside this main function, I'll not worry about what the check is for the yeah, I'll just refer to the check object. Okay, so I'll not worry about struct and all that. I'll just use auto for now. So check and then pass val And again, pretty much the same example as before. I'll set ref to 4. Check. We will use 10, 11. Change val. Let's set to 5. Check. 10, 11. Ref to 17. Check. We'll change it to 1,2. So if we compare, we have to write so much of boilerplate code so that we have a check for like check like function which you can pass values and get the same output as a lambda expression. So in these cases, lambda expressions are quite useful. They also give the same output. We'll just check that. Okay. As you expect, this is exactly what we saw before. Changing val does not change anything, and changing ref and again the parameters, we get the same output as expected. Okay. Furthermore, yeah, like I was saying, you have to write a lot of boilerplate code just for it to behave the same as a lambda expression. Okay. So we're going to get the same functor like behavior. Okay. So here a struct or a class will also do. Okay. So to make it work like a functor, so you can use a class to that will be a functor. You see that a lambda expression exactly works that way, but you don't have to worry about too much boilerplate code. It's a one-line way of just declaring the thing and then just reusing multiple times. Okay. All right. Right. So if you, I mean, that's all the I wanted to cover about lambda expressions. So if you guys have any questions, feel free to ask. Um, yeah. In the next class, we'll cover smart pointers. Okay. So which will be tomorrow. So there's an extra class. It's not next week. So today is actually the last class, but I'm taking an extra class tomorrow, Wednesday. Okay. So that will be the last class for this programming set in modern C++ day sessions. Okay, so please do join if you uh, want to get your doubts cleared on smart monitors. And I do believe that's a very important topic on C++. So yeah, please do work out the examples that I have shown. And yeah, if you have any questions, can feel free to ask. Else I'll see you guys in the next class.